Introduction. A Journey Beyond Imagination. In 1977, NASA launched the Voyager probes, twin spacecraft that embarked on an audacious mission to explore the outer planets of our solar system. These remarkable machines, powered by technology now considered archaic, have transcended their original objectives, becoming humanity's first emissaries to interstellar space. Over 4 decades later, Voyager 1 and Voyager 2 continue to captivate scientists and the public with their resilience, delivering data from more than 15 billion miles away. Despite their limited memory, 3 million times smaller than a modern smartphone, and data transmission speeds 38,000 times slower than a 5G connection, these probes remain at the forefront of space exploration. Recently, they have unveiled an impossible discovery that challenges our understanding of the cosmos, sparking renewed excitement about what lies beyond our solar system. This article delves into the history, achievements, technological marvels, and groundbreaking discoveries of the Voyager mission, weaving in the latest insights and trends in space exploration to paint a vivid picture of this interstellar odyssey. The dawn of a cosmic adventure, launch and initial mission. On August 20th, 1977, Voyager 2 lifted off from Cape Canaveral, Florida, aboard a Titan II-IE Centaur rocket, followed by Voyager 1 on September 5th of the same year. Their primary mission was to conduct close-up studies of Jupiter and Saturn, along with their moons and rings. This ambitious goal was made possible by a rare planetary alignment that occurs once every 175 years, allowing the spacecraft to use gravity assists to visit multiple planets efficiently. The Voyagers were designed to capture high-resolution images, measure magnetic fields, and analyze atmospheric compositions, providing humanity's first detailed look at the gas giants. The spacecraft were engineering marvels for their time, equipped with 11 scientific instruments, including cameras, spectrometers, and magnetometers. Their power source, radioisotope thermoelectric generators, RTGs, converts heat from decaying plutonium-238 into electricity, enabling them to operate in the cold, dark reaches of space. This design ensured longevity, allowing the probes to far exceed their initial 4-year mission to study Jupiter and Saturn. Surpassing expectations. What began as a mission to explore the outer planets evolved into an interstellar journey. After completing their primary objectives, the Voyagers continued to transmit data, venturing beyond the heliosphere, the region dominated by the sun's magnetic field and solar wind. In 2012, Voyager 1 became the first human-made object to enter interstellar space, followed by Voyager 2 in 2018. These milestones marked a historic achievement as the probes began to explore the uncharted territory of the galaxy, providing data on cosmic rays, plasma density, and magnetic fields beyond our solar system. The Voyager's longevity is a testament to the ingenuity of NASA's Jet Propulsion Laboratory, JPL. Despite their aging hardware, engineers have implemented creative solutions to extend their operational lives. Since 2020, non-essential systems, such as heaters, have been powered down to conserve energy, with projections suggesting the probes could continue transmitting data until around 2030. For the scientists and engineers who have dedicated decades to the mission, the Voyagers represent a legacy of exploration that has inspired generations. Jupiter, a world of wonders. The Voyagers' encounters with Jupiter in 1979 were nothing short of revolutionary. As they approached the gas giant, their cameras captured stunning images of its swirling clouds, vibrant bands, and the iconic Great Red Spot, a storm larger than Earth that has raged for centuries. These images, transmitted months before the closest approach, captivated audiences at JPL and the public, showcasing the beauty and complexity of Jupiter's atmosphere. The most astonishing discovery came from Jupiter's moon, Voyager. One's images revealed active volcanoes spewing plumes of sulfur and sulfur dioxide up to 300 miles into space. Pele, one of Io's most prominent volcanoes, produces eruptions 30 times taller than Mount Everest, covering areas the size of France. This finding shattered the assumption that moons were geologically dormant, revealing as the most volcanically active body in the solar system. The Voyagers also discovered Jupiter's faint ring system, a surprising feature that added to the planet's mystique. Europa, another of Jupiter's moons, proved equally intriguing. Voyager 2's observations suggested that beneath its icy crust, which may be over 60 miles thick, lies a potential subsurface ocean. This discovery sparked speculation about the moon's habitability, laying the groundwork for future missions like NASA's Europa Clipper, launched in 2024, which aims to investigate these possibilities further. The Voyager's findings at Jupiter redefined our understanding of gas giants and their moons, setting the stage for decades of exploration. Saturn and beyond, Voyager 2's Grand Tour. After Jupiter, the Voyagers used gravity assists to propel themselves toward Saturn. Voyager 1's 1980 flyby provided detailed images of Saturn's rings, revealing their intricate structure, and studied Titan, a moon shrouded in a thick, hazy atmosphere rich in organic compounds. These observations fueled interest in Titan's chemistry, leading to the Cassini-Huygens mission in the early 2000s. Voyager 1 then began its northward trajectory, exiting the ecliptic plane toward interstellar space. Voyager 2, meanwhile, embarked on an extended mission to Uranus and Neptune, a feat made possible by precise gravity assists. In 1986, it became the first and only spacecraft to visit Uranus, discovering 10 previously unknown moons and revealing the planet's pale cyan atmosphere. 3 years later, Voyager 2 reached Neptune, capturing images of its deep blue, methane-rich atmosphere and recording wind speeds of up to 1,000 miles per hour, the fastest in the solar system. The flyby also showcased Triton, Neptune's largest moon, which harbors ice volcanoes that eject nitrogen gas and icy particles, with surface temperatures plunging to minus 391 degrees Fahrenheit. These encounters expanded our knowledge of the outer solar system, highlighting the diversity and dynamism of its planets and moons. The Voyager's images and data remain the only close-up observations of Uranus and Neptune, serving as a critical reference for astronomers. The impossible discovery. Unraveling the heliopause. Crossing the cosmic boundary. One of the Voyager's most significant achievements was their crossing of the heliopause, the boundary where the solar wind gives way to the interstellar medium. Scientists had long debated the heliopause's location, with early estimates placing it as close as Jupiter and later projections by astronomer Bill Gurney in 1993 suggesting a range of 116 to 177 astronomical units, AU. Voyager 1 reached the heliopause in 2012 at approximately 121 astronomical units, followed by Voyager 2 in 2018 at a similar distance, confirming Gurney's predictions with remarkable accuracy. The heliopause crossing revealed unexpected phenomena. Voyager 1 detected a sharp increase in plasma density, indicating its entry into interstellar space, but observed no significant change in the magnetic field's direction. This puzzled scientists, as a shift was expected when transitioning from the Sun's magnetic influence to that of the interstellar medium. Voyager 2's data corroborated this anomaly, deepening the mystery. Additionally, the heliopause's position, did not align with predictions based on the Sun's 11-year solar cycle, which influences the solar wind's strength and the heliosphere's extent. A new understanding of the cosmos. Recent analyses, incorporating data from both Voyagers, suggest that the heliopause is a dynamic, turbulent region shaped by interactions between the solar wind and the interstellar medium. Scientists now hypothesize that our Sun is transitioning from a hot, ionized region of the galaxy to a partially ionized zone, possibly influenced by ancient supernovae. These stellar explosions may have heated the surrounding medium, creating a complex boundary likened to a turbulent seaside with mixed magnetic fields. This impossible discovery has profound implications. It challenges existing models of the heliosphere and underscores the need for refined theories to explain its behavior. The Voyager's observations have also highlighted small-scale turbulence near the heliopause, providing clues about the interplay between solar and interstellar forces. As of 2025, researchers continue to analyze this data, leveraging advances in computational modeling and machine learning to simulate the heliosphere's structure and dynamics. These efforts are informing plans for future interstellar missions, such as NASA's proposed interstellar probe, which aims to explore the heliopause in greater detail by the 2030s. Technological marvels, engineering for eternity archaic, yet resilient. The Voyager's technology, while outdated by today's standards, is a marvel of durability. Their onboard computers, with a memory capacity of just 68 kilobytes, rely on an 8-track tape system for data storage, a relic of the 1970s. These tapes, designed to withstand extreme temperatures, cosmic radiation, and the vacuum of space, have preserved critical scientific data for over 4 decades. The probe's stability, achieved through a rotation rate 15 times slower than a clock's hour hand, minimizes image blur, ensuring high-quality captures during high-speed flybys. The Deep Space Network, DSN, a global array of radio antennas in California, Spain, and Australia, is the lifeline that keeps the Voyagers connected to Earth. These massive dishes, some up to 70 meters in diameter, capture faint signals from billions of miles away and transmit commands to adjust the spacecraft's instruments. Operating 24/7, the DSN ensures continuous communication, enabling scientists to monitor the probe's health and receive their data. Recent upgrades to the DSN, completed in 2024, have enhanced its sensitivity, allowing NASA to maintain contact with the Voyagers as their signals grow weaker. Gravity assists. Cosmic choreography. The Voyager's ability to visit multiple planets owes much to gravity assist maneuvers, a technique that uses a planet's gravitational pull to accelerate and redirect a spacecraft. These maneuvers, executed with pinpoint precision, allowed the probes to conserve fuel and achieve the velocity needed for their grand tour. For example, Voyager 1's swing by Jupiter increased its speed, propelling it toward Saturn, while Voyager 2 used successive assists from Jupiter, Saturn, and Uranus to reach Neptune. The complexity of these maneuvers cannot be overstated. A miscalculation in angle or speed could have sent the spacecraft off course, jeopardizing the mission. Yet, JPL's engineers mastered this cosmic choreography, ensuring the Voyager's success. This technique has since become a cornerstone of interplanetary exploration, used by missions like NASA's Parker Solar Probe and the European Space Agency's Bepi-Colombo. A message to the stars, the Golden Record. The Voyagers carry a unique payload, the Golden Record, a 12-inch gold-plated disc containing sounds and images representing Earth's diversity. Conceived by astronomer Carl Sagan, the record includes music from Bach to Chuck Berry, greetings in 55 languages, and natural sounds like wind and thunder. It also features 115 images depicting human life, culture, and the planet's landscapes. Encased in an aluminum cover with instructions for playback, the record is a time capsule intended for any extraterrestrial civilization that might encounter the probes. Sagan's vision extended beyond science. In 1990, he persuaded NASA to turn Voyager 1's camera toward the inner solar system, capturing the iconic pale blue dot image. Taken from 3.8 billion miles away, it shows Earth as a tiny speck in the vastness of space, underscoring humanity's fragility and interconnectedness. This image, updated with enhanced processing in 2020 to mark the mission's 40th anniversary, remains a powerful symbol of our place in the cosmos. The future of the Voyagers. A legacy unfolds what lies ahead. As of May 10, 2025, Voyager 1 is traveling toward the constellation Ophiuchus, while Voyager 2 heads toward Cetus. Their RTGs are expected to deplete by around 2030, after which they will cease transmitting data. However, the probes will continue drifting through space, potentially enduring for millions of years. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese, 445, and Voyager 2 will approach Ross, 248. Though the odds of an alien encounter are slim, the golden record ensures that a fragment of humanity's story travels with them. The Voyager's data continues to shape modern space exploration. Their findings at Europa and Titan have inspired missions like Europa Clipper and Dragonfly, a drone set to explore Titan's surface in 2028. The heliopause data is informing the design of future interstellar probes, which could launch within the next decade. Additionally, advancements in artificial intelligence are being used to reanalyze Voyager data, uncovering new insights about the solar system's boundaries. A cultural and scientific legacy. The Voyager mission is more than a scientific endeavor. It is a cultural touchstone. Its images and discoveries have inspired books, films, and art, from the 1984 film Starman to the 2017 documentary The Farthest. The mission's ethos of curiosity and resilience resonates in an era of renewed interest in space exploration, driven by private companies like SpaceX and Blue Origin, as well as international collaborations like the Artemis program, which aims to return humans to the moon by 2026. The Voyagers have also sparked philosophical reflections on humanity's place in the universe. The pale blue dot image, coupled with Sagan's eloquent commentary, reminds us of our shared responsibility to preserve our planet. As climate change and geopolitical challenges intensify, the Voyager's legacy underscores the importance of unity and exploration in addressing global issues.